Okay, so we've done some hard work in learning about Markov chain Monte Carlo algorithms and learning about how to use derivatives in order to build possibly better samplers. And so now we're going to talk about, well, what happens when we don't have derivatives at our disposal, but we still want to employ better proposals, better algorithms, so that our samplers move around quickly. And so far, we've had gradient-based MCMC algorithms for target densities pi of x proportional to some e to the power minus u of x, where u, we've sort of assumed to have some properties. The first property we've assumed is that u we've assumed is differentiable because we have employed derivatives, right? We've also assumed essentially that that u has a Lipschitz gradient, or its gradient is Lipschitz, and we've implicitly assumed it in the sense that when we're employing a Langevin-style algorithm, we want to ensure that the discretization that's employed actually works well. And that happens when the gradient itself behaves not faster than a linear function. And then we've also established in the last lecture, we also established instances when U was strongly convex, in fact, M strongly convex. But then what if U is not differentiable? And it's not like a hypothetical situation. It's actually extremely common for U not to be differentiable. So recall, U is the potential or the part in the exponent without the negative of a target density. And in many, many modern models, U is often not differentiable because non-differentiable functions, particularly non-differentiable prior distributions, induce some sort of sparsity in the model, pushing parameters towards zero. And so when parameters are pushed towards zero, that means they don't require estimation. And so you sort of reduce the number of unknown parameters in the model because some of the not so important ones are pushed to zero. So it's a way to do some sort of naive dimension reduction, a way to do some sort of naive, sort of informed variable selection, and so on. Okay, yeah?
One thing I've asked that the measure of
RD and absolutely continuous with respect to Lebesgue.
Work whenever we define gradient of space.
I think so. I think the people again have done something called like the Langevin dynamics on manifolds, and there's some work there. I'm not sure if they've done this for proximal mappings or not, as in for non-differentiable objects on those. So that literature I'm not aware of, but for differentiable functions, there's the whole Langevin dynamics on manifolds as well. Okay, so that becomes, so like for example, a very popular model is the Bayesian lasso model, which sort of does linear regression, pushing the slopes of the lines in the linear regression to zero for some of the components. And that's what the L1 penalty over here does. And so with the L1 penalty, the U potential becomes non-differentiable. Another very common problem is a constraint posterior. So if my support is assumed to be on all RD, but if it is not on all RD, which means there's some part of it that on which I don't have support for my target density, then I naturally don't have a differentiable potential, just by definition. In which case, what you can do is we can write U as my original, my sort of unrestricted part of the potential, plus a constraint that basically makes this infinity outside of the constraint set. So if the potential is infinity out of the constraint set, that makes the target zero, right? The target density zero. So that's one way that we have non-smooth potentials. And then there, in addition to the lasso regularizer, which is an L1 convex regularizer, there's like a whole horde of regularizers in both as Bayesian priors and as model fitting strategies in high dimensional settings. So all of this is to say that the fact that U may not be differentiable is not a figment of our imagination. It is actually a reality in many different problems. So we do want to do a gradient-based MCMC method when grad U does not exist everywhere. And so our solution to this is to say, okay, U is not differentiable anywhere. And so a popular solution implied is let me approximate U with some smooth approximation that is hopefully a reasonable approximation of U, but it is smooth. And then I'm just going to use the gradients from that approximation. That seems like a very obvious first hack at the problem that turns out to be quite reasonable. Obviously, a lot of it depends on what kind of approximation you're employing. Right? So the key is I take my objective, which is my potential function U, which is non-differentiable. I approximate it everywhere pointwise with a differentiable function, and hopefully that approximation is good. Right? And so this is going to be done, this approximation is going to be done using Moreau-Yoseda envelopes. And I showed these next couple of slides in the intro talks a couple of months ago, but we'll revise this again. So here's my assumption. My assumption is U is convex. And so that's an assumption I'm going to have to not make eventually. So that's the direction we're moving in. Eventually, we want to do everything for non-convex, or at least some class of non-convex functions. But at least for now in the literature, often U is convex and lower semi-continuous, and pi is proportional to e to the power minus ux. The Moreau-Yoseda envelope for some parameter lambda greater than 0, that is your approximation parameter, that tells you how much approximation you want to impose, of u of x is going to be denoted as u lambda x, and that's the infimum over y in all Rd of u of y plus an L2 deviation penalty from x with a constant 1/2 lambda. And so this does look, I mean, there's a way that one can interpret it, but that might take a little while. So instead, I'm going to try and show a visualization, which is again a visualization we discussed a couple of months ago. But if we just fix pi of x to be proportional to e to the power minus absolute value of x, so absolute value of x is a non-differentiable function, but e to the power minus this is the common Laplace or double exponential distribution. And so what I'm going to do now is this is my u of x function. This is an absolute value function. And u lambda x is going to be my approximation. And the way this approximation is built is it says it takes the inside function, the function that's inside the infimum, and I'm going to plot that function for different values of x, for different values of y as a function of x. So as a function of x, this inside function is just a parabola, right? Because it's x minus y squared plus a constant. Right? So as a function of x, this is a parabola that has its smallest value at y. Right? And so at different values of y, the parabola changes. And so we can visualize what this parabola looks like. And so for example, y equals minus 2, the minimum of the parabola happens at x equals minus 2. And the height is exactly u of y, u of minus 2. And this is the shape of the parabola. Right? And then I can plot, again, the inside of the function for different values of y again. So I can do that again for y equals minus 1.5, y equals minus 1, y equals 0, and so on. And I can fill the grid up. Right? And once I do this, what I realize is, okay, now what I need to do is I need to take, for any given value of x, I want to take the infimum over all values of y. So that means for any given value of x, I'm going to go up and see where's the first blue curve that I meet. Right? That's the smallest value of u of the inside function. And that's going to give me my final envelope pointwise for all value of x. And that looks something like this. Right? So that just basically joins all the curves over here. And this is at least in we have this available in closed form for the absolute value function, and this turns out to be the Huber loss function. So what are some nice properties of these Moreau-Yoseda envelopes when G is convex? Because we're going to rely on these properties to not only prove our results, but to ensure that we're doing something sensible when we're running our algorithms. So if U is proper, lower semi-continuous, and convex, then for any lambda, lambda tells us the approximation. U lambda is going to be continuously differentiable even when U is not. So if I give you a non-smooth U function, U lambda will be smooth. I'm assuming U is convex. That's great. That means I can take derivatives. The gradient of U lambda actually is available to me in a very nice clean form. It's 1 by lambda x minus prox of x for U. Now, I forgot to put this on the slides. I realized the prox is nothing but where the minimization is actually happening. So let me go back. The prox is basically the value of y that minimized this function. That's the proximal mapping. Okay, I should have mentioned that, I forgot. So the grad U lambda x is in this nice form. It's x minus prox. Yeah, exactly. So this is assumed to be convex. And as a function of y, this is strongly convex. So now this whole inside function is strongly convex. So there is a minimizer. The other very nice thing is, irrespective of what U is, grad U lambda has a Lipschitz continuity constant of 1 by lambda, which means its gradients is our Lipschitz with constant 1 by lambda. So as lambda goes to 0, I am getting highly relatively non-smooth because this constant is increasing, but as lambda increases, I'm getting a smoother and smoother function. And one really important thing that is not very useful in the MCMC implementation, but turns out to be very useful in a different area called importance sampling, is the fact that, oh, this should not be grad, sorry. This is without the grad. So the envelope U lambda x is always less than equal to U of x. So the envelope itself is less than equal to U of x. So this shouldn't be grad. So we saw this because the red Huber curve was below the absolute value function. The other very nice property, which for any approximation is a great thing to have, is that as you push lambda equal to 0, my approximation is going to converge to U of x. I think this is a find and replace error. Yeah. This again is grad. It should not have been grad. It should just have been U lambda. Sorry, this is not gradient. So this is saying that the envelope itself, the approximation will converge to U as lambda goes to 0, which is great. U and U lambda have the same minimizers. So if I go back to this function, I see that the envelope is lower than the absolute value function, and they share the minimizer as well. Right? So that's also a very good property. And U lambda is convex. Not grad U lambda. U lambda is convex. This is a find and replace problem. Okay. So that's really useful as well, because a lot of times we are relying on convexity of the potential to come up with some nice results. And the fact that U lambda is convex, it turns out to be a very useful property. Another really useful property is that actually for the envelope itself, if U is convex, we have integral e to the power minus U lambda to be finite, which means we have integrability. Now, if I have integrability, then that tells me if I exponentiate this and I set this to a pi lambda with a proportionality, that tells me pi lambda is a valid density. Okay? And this becomes really useful because corresponding to the envelope, I have a density function, which means now I can sample potentially from this density function if that's what we want to do.
So this last thing means that because your U lambda is below it, so the e to the minus U lambda is going to be bigger, but it means uniformly you are having a good approximation so that this integral is still working for you.
Yes, exactly. I mean, so the e to the power minus U lambda x is always going to be bigger. But then if you integrate it and normalize it by the appropriate constant, then you get that it has some tail behavior that ensures that it integrates. And I'm going to go back and look at the gradient formula again, because this is actually really useful, because we need to look at the gradients, right? I'm going to run a Metropolis Hastings algorithm employing the gradients of my approximation. And so we should look at the gradient of the approximation. And so the gradient is x minus the prox value, the actual place that the minimizer exists, by lambda. And this is quite useful because there is no need to now differentiate u itself, right? I don't need to go and look for the derivatives of u where it is differentiable. I can just look at the proximal mapping. And then computing this derivative gradient might reduces to solving the proximal minimization problem, which is a strongly convex problem, which is an easier problem potentially to solve than minimizing or finding a good optimizer for u. But it's not all very easy. So for example, if we might have a closed form solution, if u itself looks like some nice function like the L1 function where we had like a nice Huber loss as my Moreau approximation, or a lot of other functions like the indicator function for the constraint spaces, there the envelope is available, the proximal mapping and the envelope are available tractably. So I just need a quick calculation on pen and paper, and I have essentially the gradient for free because I just need to write a code that evaluates it. And I would have had to write a code that evaluates the gradient of a different function, the original function as it is. So it's just it doesn't require any other iterative procedures. But often there are some functions where you might then require an iterative solver because the whole point, the obtaining of this proximal mapping requires an optimization problem. And if that optimization is not available analytically, then we might have to resort to an iterative solver. So where have people used this type of approximation? So one of the first works, it's unclear which one came first because there's the archive and the publishing, but one of the first most cited reference as one of the first work is the work by Marcelo Pereira in 2016. And what they did was said, we're going to use the gradient of u lambda x in the Mala proposal to sample from pi. So let's unwrap this. Let's see what this means. It means that they're going to now say that to sample from pi, I'm going to get y from normal x minus h by 2 grad u lambda x. So I'm replacing the original gradient of a function that's not differentiable with the derivatives of a smoother function, which is an approximation. But then I'm going to do accept reject with probability alpha, but here alpha is minimum of 1 comma pi times q by pi times q. So it's not pi lambda, but it is pi. And that's because we want to sample from pi. So in the first lecture, we saw that it is because of exactly this acceptance probability that the Metropolis-Hastings algorithm was pi reversible or had satisfied pi detail balance. Whatever is the pi here, the algorithm will be reversible with respect to that, and it's going to keep that distribution as a stationary distribution. So if instead I use pi lambda here, then the sampler is going to get samples from pi lambda, not from pi. But we want samples from pi, and we've used approximation u lambda only for the gradient. And then the other key thing is that I know that all I need for the Metropolis-Hastings algorithm to be ergodic, to converge eventually to the stationary distribution, is that the proposal should just always be positive everywhere. Okay? Which in this case, as long as gradient doesn't, eat up something over here or blow up in some very weird ways, this is always going to have support on RD. Okay? And so what this tells us is that the sampler, almost by the structure of Metropolis-Hastings algorithms, is going to be reversible for pi and is going to converge to pi. And so what Marcelo Pereira went on to do is, because of certain reasons, set lambda to be h by 2, because now recall, I need a quality of approximation as well. How do I actually choose lambda? And they set lambda to be equal to h by 2, and it's not exactly clear whether that's a reasonable choice for this particular structure. But that's what it was, and then went on to show similar results to geometric ergodicity as the results I discussed in the previous lecture that came for the Mala algorithm from Roberts and Tweedy. So there is some sufficient conditions that says, even though you replace the true gradient with a gradient of an approximation, you will almost under very similar conditions, you will still converge at a geometric rate to the distribution of interest. And in this particular case, one sort of con is that because they're employing this here and U is the potential of the full posterior, in many cases, grad U lambda x is not completely tractable in closed form. And so there is an underlying iterative algorithm that needs to be called for every single step of the Markov chain. And so that's not ideal. And so there's another way of thinking about Moreau-Yoseda approximations, and this could almost feels like a like the natural thing to do. So a common structure for various potentials is of the form U of x is f of x plus g of x, where f is like the smooth part of the potential and g is the non-smooth part of the potential. And this happens quite naturally in our Bayesian models because f will correspond to the negative log likelihood, for example, and g will correspond to the negative log prior. Right? So you have a prior that's typically going to have the non-differentiable components, and that gets encoded in g, and the likelihood is typically smooth, and that gets encoded in f. It's not necessary, we can swap that as well, but it's typically what happens. And so if I assume this structure and f has, Lipschitz gradients, but g is non-smooth, then a natural thing that seems we could do is we just envelope g. Why do we envelope f at all? F is smooth, it has nice properties, I can just envelope g. So then I'm only enveloping part of the function, so most of the gradient is true to what it needs to be, and only part of it is what I'm enveloping. And so there's popular models where this decomposition holds. So for example, the Bayesian lasso, we have like the original OLS loss function, and then the L1 penalty. Then in any constraint problem, I might have the negative log likelihood, negative log posterior times the constraint function that's encoded as whether my parameter is in the constraint set or not in the constraint set, the indicator function. Or I might have something called the sparse plus group-based lasso or penalty, which is the negative log likelihood plus some combination of an L1 and L2 prior, or an L1 and grouped L2 prior. Right. So now this sort of composition framework was proposed by Alain Durmus and Eric Moulin and Marcela Pereira. Said, okay, now I'm going to use this composite setup and I'm going to define U lambda x, my approximation, as f of x plus g lambda x. So f remains the same, but I'm going to envelope g instead now. And now I'm going to do my ULA. If you recall, ULA was the unadjusted Langevin algorithm. So you discretize the Langevin SDE, and then you get the ULA algorithm. So now they're going to just apply ULA to the smoothed target pi lambda, which means they're going to do xk plus 1 is equal to xk minus h by 2 of the gradient of this U lambda x. But the gradient of f is available to me, and the gradient of this G mapping is available as well because of the properties of the Moreau-Yoseda envelopes, plus my Gaussian noise. Okay, and so the total error decomposition, if I'm running this chain, because recall ULA is an approximate algorithm, it will not converge to pi for any fixed size of discretization. The total error decomposition in TV distance from any time k to pi can be broken down to the error coming from the ULA itself and the error coming from the fact that pi lambda is not pi either, right? There's an approximation there as well. So now maybe lambda needs to go to 0 as well as my step size needs to go to 0. And again, much of this construction relies on the fact that G is convex. Okay. So there are other examples as well, and I just wanted to make sure I mention. There's more, but there's another one that's and I discussed this very briefly last time, is HMC, which is the Hamiltonian Monte Carlo algorithm, which you can view as essentially many steps of a mala within one step of the algorithm. So if you do many steps of mala and call that one step of the algorithm, that's similar to what HMC might be. And so Chari et al. Did two different algorithms, but one of them replaces the full gradient in HMC with the Moreau envelope gradient. But then because I'm employing multiple gradients within one step, Now the gradient calculation is even more expensive because every step requires many more gradients. And so now you need to ensure that there is an analytical form of the gradient available. If it's not, then it's going to be extremely computationally intensive to implement such an algorithm. And that's exactly sort of what happens. And so recently, one of my PhD students and a friend, Eric Chi, we sort of said, okay, well, we can do the same thing here by breaking up the gradient of, so by doing the composite method where we take the gradient of f and the gradient of the Moreau envelope of G. And if this is the gradient, and the Moreau envelope of G is available to us attractively for various different functions, because that's the simpler part of the function, this becomes a relatively cheap calculation. And then what we were able to do is we were able to also arrive at conditions for geometric ergodicity that are very similar to the conditions I discussed for Mala itself, where we said the tails of the distribution need to diminish, but not too quickly. And then we also were able to propose a way to choose the lambda as well. And I mention these because these are going to feed into our objectives for our project as well. So the question now is, everything so far has relied on the fact that either G or U, depending on what you're enveloping, requires convexity. And so where do we require convexity in that construction exactly? Well, the first reason is the proximal operator is well defined when I have a convex function. Like the question asked, because U is convex, or the function you're enveloping is convex, and you're adding a strongly convex function to it. Now, when you're optimizing it, the proximal mapping exists, and it's unique. So for convex G, prox G is unique for every x. For non-convex G, the proximal minimization may have multiple minimizers. And we'll see an example of this in a couple of slides. Another reason is that the Moreau envelope inherits convexity. So because G is convex, U lambda is convex. And that turns out to be, again, very useful because I'm employing gradients of this object. And another reason, although not directly related, is that if I don't have a convex function, if I have a multimodal function in my target density, then doing any sort of theoretical analysis becomes really, really difficult because most of it relies on definitely unimodality of my target, but then often also log concavity of my target. And so that's why, at least from a theoretical perspective, imposing conditions such as log concavity of the target makes much of the analysis exponentially easier. So what are the models that need non-convex proximal MCMC? And as it turns out, actually in Bayesian statistics, there's lots and lots of priors that impose a non-convex prior structure, which is akin to a non-convex penalty. And so, for example, and I'm not going to give a mathematical formulation of them, but there's, just to convince you that this is, again, a problem that exists, is there's a popular SCAD penalty and the MCP, which is the minimax convex penalty. These are very common penalty functions, or when I say penalty functions, you can think of them as priors as well, that are naturally going to be weakly convex, which I'll explain in a minute, but non-convex. There's also deep learning priors and neural network-based priors that are non-convex, but in some cases they are not convex, but they have enough structure that you can do something with them from the point of view of convexity. In many imaging inverse problems as well, there are lots of Bayesian compression-based priors that impose non-convex priors. And then mixture models or multimodal posteriors, not always, but sometimes can be viewed from the point of view of a simplifying assumption of weakly convex functions. And so those become very obvious non-convex target densities. So what we're going to do is we're going to restrict ourselves to the class of weakly convex functions. So we'd ideally like to do all non-convex functions, but that's sort of like, we haven't learned to walk yet, and I'm going to run a marathon. And so what we're going to do is instead say, okay, let's try and figure everything out for weakly convex functions. And once we have an understanding of what happens for weakly convex functions, there's some hope to maybe extend it to non-convex functions. So what's a weakly convex function? A weakly convex function is a function that may not be convex. It can be convex, but it may not be convex. But if you add enough of a quadratic to it, it becomes convex. So g of x may not be convex, but g of x is weakly convex. If you add rho by 2 x squared, then this is convex. Another way of thinking about it is this: its Hessian is larger than minus rho. Sorry?
All this coming definite order.
This one?
Yeah. So that larger than equal to what? Is the major.
That's right. So minus rho ID, right? So yeah, okay, sorry. This means this matrix plus this matrix is positive definite.
Exactly.
Yeah. So that ordering is a PD ordering. Yeah, thank you. So again, examples of weakly convex from the class before is, well, convex functions have rho equals 0, so they're naturally weakly convex. So anything we do for weakly convex applies to convex functions. The SCAD and the MCP penalty, these are fairly popular penalties in the regression space, are weakly convex, and there's a lot more that I haven't included because I'm not giving you a lot of context about them. So shockingly, after I proposed this project in the last couple of months, I've seen a lot of work that's come out within the last couple of months. So some very, very recent work is the following. So when lambda is less than 1 by rho, I found this yesterday night, but I'm happy it's 2025b and it's on arXiv yet, so it's from November of 2025. Present many properties of weakly convex functions. So this is great, and we'll go over these with my group today. Some nice set of properties that are neatly presented with proofs that make our life much easier. Then this is a paper from January of this year. This is called the DAS algorithm, the diffusion at absolute zero algorithm, which again work with weakly convex functions. And this seems to be the first algorithm that actually gets non-asymptotic rates of convergence. But they're doing something different. They're using an unadjusted algorithm, and they're adapting lambda, as in they're letting lambda go to 0 as well, in a very particular looping structure. So that's all I'm going to say, but just to let you know that this is, again, fresh, hot off the press of arXiv. And then this almost same set of folks over here. Now this is a NeurIPS paper from the last NeurIPS. Studied non-asymptotic rates for proximal stochastic gradient Langevin dynamics. I mentioned this in my previous talk, where if I have massive data, I might not have access to all gradients, so I will replace the full gradient with a gradient of some of the observations instead of all of the observations. And that's a stochastic gradient implementation. And again, they study non-asymptotic rates. There is, though, no work that I have found, but who knows, we'll see this. Some of this was a revelation, but no work in corrected Langevin algorithm. So a lot of this is work that's coming from, again, the machine learning perspective, where it's too expensive to evaluate the acceptance ratio. But then if we're working with MH algorithms that need to be exact, then there's no work understanding, well, when are these algorithms going to be geometrically ergodic? Are we giving too much away in the approximation that now the Mala algorithm is doing something close to ridiculous? And so some of the key results that we identified from this first paper, or I guess second paper, for weakly convex function, when lambda is less than 1 by rho, rho is the amount of weak convexity, the prox is single valued. So that means that I'm going to have a unique minimizer, and this comes from the fact that we have strong convexity. And before we saw this, our group sort of figured this out 2 days ago. U lambda is differentiable with grad U lambda being exactly the same as before, so that's great. So that means my approximation is smooth, and I have the same gradient as before. Now my Lipschitz constant for this gradient function is now slightly different. So I have 1 by lambda, 1 minus lambda rho instead of just 1 by lambda. And U lambda continues to preserve critical points and minimizers of the original function. Okay, so that's pretty neat. Which means the fourth implies that it is not necessarily convex. If there are 2 minimizers, then U lambda is going to preserve those 2 minimizers. The Lipschitz constant is 1 by lambda and 1 minus lambda rho in the denominator, and this is larger than 1 by lambda. And so this gets worse as you get as lambda rho goes closer to 1, which means as you go closer and closer to that, you're going to get less and less of a smooth function. And then this condition seems critical because what this condition ensures is inside the proximal calculation, so inside the inf function, what you have remains convex. Right? And so that means you can actually evaluate and get the proximal mapping analytically. So the story from this slide is that despite not being convex, U lambda is smooth, and so gradient-based MCMC is applicable as long as lambda is less than 1 by rho. Right? And we can see this, so some of these plots were made by our group yesterday, this is the MCP penalty function, which is the minimax convex penalty. Which one is it? So I've just like thrown it in front of you. So the UY is this function here, and you can see that it is unimodal or one minima, but it is not convex, right? So this part here starts becoming concave, right? And so as I increase lambda, I get this type of approximation, and these are still not convex, but at some point I see that they may be convex, we're not sure. So you increase lambda large enough, you might get some convexity, but we're still trying to prove that. But something interesting happens. So I said that lambda has to be less than 1 by rho. In this MCP thing, 1 by rho is alpha. So as long as lambda is less than alpha, my proximal mapping is unique. So when I said alpha is 2, so when I said lambda equals 1, I get this blue curve over here as the proximal mapping as a function of x. So as x changes, this tells us what the proximal mapping would be, and this tells us what your gradient would be, right? So for example, here, the gradient is x minus prox, which because this is the x equals y line, the gradient is 0, right? The gradient is 0 over here as well. But then here, there is some gradient, and then this is the actual prox function. But you see what happens when lambda is equal to alpha and when lambda is greater than alpha is at these 2 points, this is no longer a function. Right? I mean, for the same point, you have multiple values of the prox. So this is not a jump, it's multiple values of the proximal mapping. So at this value over here, at x equals like minus 2.3, the proximal mapping is a set of all of these points. Right? And that's really the problem if you choose lambda greater than 1 by rho. Okay, so what is it that we want to do? What's our proposed approach? The phase 1, well, the goal is still to this is pi proportional to e to the power minus u of x. Sorry. U of x, though, is rho weakly convex and possibly non-differentiable, right? This is our problem statement. I still want to sample from a pi, but its potential is rho weakly convex and possibly non-differentiable. Solution is to employ Moreau-Yoseda envelopes for lambda less than 1 by rho, but we are going to do the accept reject, we're going to do the corrected algorithm because we want to sample from pi, not from some coarse approximation. And the steps, well, the first for us was to review and establish properties, and lo and behold, yesterday night we found this, so that makes our life a little easier. We've already done some of that ourselves. We want to be able to implement one proximal Malai example so that there's a proof of concept that this actually works, doesn't break down. And we want to arrive at conditions for geometric ergodicity. Again, going back to the first talk, we want to ensure we take this back to a practitioner who can rely on the fact that a CLT, a central limit theorem, can exist for all of their estimates. And then most critically, all of this is assuming some lambda, choose whatever lambda, and then, things might work. But then a practitioner would ask us, well, what should I set lambda to be? And so there needs to be some guidelines. And so we need to understand how should lambda be chosen. That turns out to be really important. And so we hope that for some of these, we'd give you an update on Monday. Right? And the phase 2 is to see, well, can we do this for any lambda? So the main problem is that the proximal mapping is a set after lambda, if lambda is large. And so is there a way, because we're doing an MH, we're doing a Metropolis-Hastings correction, and we've established that even a nonsensical proposal might still theoretically work. What does it just mean for it to not work very well? It means that there might be some areas where it doesn't work well, but in general, it works well. And so if we can still study the algorithm for any lambda, then we'd want to do the exact same things, except we'd need to construct the sampler and tell it what to do when your prox is not unique. And that requires some careful development. But that might happen post this workshop, right? That'd be phase 2 once we have a proof of concept for phase 1. Okay, so we went over an introduction to MCMC in Metropolis Hastings for a wide variety of problems. Then we zoned in and said we'd want to make these algorithms a little better, and that can often be done by utilizing gradients. And so these algorithms now with gradients sample fairly well. But then here's a problem that many of my potential functions don't have gradients. So can I do something else gradient-like to be able to run still very good samplers for these subset of problems? And then our goal is to say, okay, now I may not have differentiability, but often I actually don't even have convexity. So can we establish an extension to that framework? Thank you.
Thank you, Dootika. Thank you very much for this overview. Questions?
So this is like something Raghav and I have done work on, understanding how to maximize functions on large networks. Would this sort of, as long as you compute gradients and networks, would this thing work, I think? Or like I'm still puzzled to see what about the space you've used? Use gradient definitely, norm definitely.
Yeah, the space we've used predominantly in the definition of the proximal mapping. Because the Moroi-Oseda envelopes are traditionally defined on RD. So, but I don't know the literature beyond RD or aside from RD. So that's mainly why, I mean, we've fixed it to RD. But the other reason, obviously, is for a lot of problems that, like, you know, Bayesian statisticians worry about, we are often in RD. But that would be the thing, is to see, well, is there an idea of proximal mappings or these envelopes beyond this? There's also other smoothing techniques, like people do like Gaussian smoothing or modification and things like that. But those are then very difficult to work with from like the sampling perspective, because you can't really evaluate those. But they might be maybe effective in like the network case, because you're sort of Gaussian smoothing over a finite set of points.
Sorry.
The JKO scheme in the Wasserstein space is essentially just this Moroi-Oseda in that case. So we can define an analog on that on the Graphone space as well. So analyzing this is something that needs to be done, but this can be defined.
I see. Okay. Thanks, sir.
You have not been talking about rates of convergence as your lambda goes to its limit. Are they around?
Yes and no. So let me go at least here. Where do I want to go? Yeah. So this paper, and it's a very nice paper to read as a review, because it's a review article, says that bounds this. So the TV distance between pi lambda and pi is linear as a function of lambda, but also has the Lipschitz constant of g next to it. So it's essentially less than equal to lambda times the Lipschitz constant of g.
Okay, so that's very nice then.
Yeah.
Yeah. Further questions? Okay, thank you, Dootika.
Thanks.